Okay, good afternoon, everyone. So this is the tutorial for week 3 and week 4 on linear systems. So we start with question 1. So I assume that you have these questions already downloaded from Moodle. So now I will share my piece of paper, okay, because all the theory can be worked on a piece of paper, okay. So now, so if you have any question, please put into the chat box. Okay, so let me try to open the chat box. Yeah, so now I'm going to start with question 1. So question 1. So week 3 tutorial MATH2301. So question number 1, what is the definition of a norm of a vector? So X is a vector in Rn. So X is a vector in Rn, so it can be written as n tuple x1, x2 up to xn. So all of them are real numbers, and this one is in Rn. Okay. So what is the definition of the one norm? Well, so if you remember the formula in the lecture notes, yeah, then the one norm is just the sum of x1 in absolute value, x2 dot up to xn, right? And what is the two norm? So the two norm is just x1 square plus x2 square up to xn square. And do not forget the square root. Okay. And then what is infinity norm? So infinity norm is just take the max of all the entries in absolute value, j from 1 to n. Okay. So it's the definition. So now the next question is plot the following set. So now, so this one is part 1, yeah. Part 2 is now you plot, say B1 is x in, well, here we just plot on the plane, okay? So just take n equal 2. And the one norm is less than or equal 1. So how do you plot this? Well, maybe let me expand this a bit, yeah? So this one is just x1, x2, yeah? And so that x1 in absolute value plus x2 in absolute value less than or equal 1. Okay. So suppose I have a plane like this. So let me draw a plane here. So x1 here and x2 here. Then how does it look like on the plane? How does it look like on the plane? Okay, so maybe let me give you a hint, okay? So suppose you want x1 positive and x2 positive, right? So you consider the first quadrant here. And then what is the region that satisfies x1 plus x2 less or equal 1? So what is this region? No, it's not a circle. x1 plus x2 less or equal 1 is not a circle. It's a region underneath a line, yes, but what line? Yeah, where's the line? Where do I draw the line? Yes, the line x2 equal x1 minus 1. Well, actually, it should be x2 Well, because you have x1 plus x2 equal 1, right? Yeah, so actually it should be, so if you move, if you do like this, then x2 should equal minus x1 minus, yeah, okay, so minus x1 plus 1, yes, it's correct, yeah. And this line will be, you know, it's going to be when x1 equals 0, then x2 is 1, yeah. And when x2 equals 0, then x1 is 1. So this is the the line that go through those 2 points. Okay, and we consider only the first quadrants, yeah. And then the region that less or equal 1 is this region. Okay, and you can consider other region as well. So you can consider other regions. So suppose x1 greater or equals 0, but x2 less than or equals 0. Yeah. Then you see, I mean, now the problem is x1, the absolute value of x1 is still the same as x1, but absolute value of x2, because x2 is negative, so you have minus x2 less than or equal 1. Okay. And then you have, so in the second quadrant, I mean, in this quadrant, then this line will become like this. Yeah, the line is x1 minus x2 equal 1. Okay. And hence you can do the same in 4 quadrant. Yeah, so then you get a diamond like this. So this will be your set B1. Okay, so this is minus 1, 1, 1, and 1. Yeah. So now what happened if I replace B1 by B2? Okay, so B1 is for the 1 norm, but B2 is for the 2 norms. So the B2 will be x in R2, and the 2 norm is less than or equal 1. So I can write down this more explicitly. So this one x1 comma x2 and x1 square plus x2 square. And I take the square root, yeah, less than or equal 1. But then if the square root less than or equal 1, when I raise to power 2, it's still less than or equal 1. Okay. So what is this set? So what is B2? A circle. Okay, so now it's correct. Because this is just a line. I mean, this is the equation of the circle. And the circle has radius 1. Yeah. So this one is just exactly the circle radius 1. Yeah. And inside the circle, then we call it a disk. So less than or equal. So on the circle, then we inside, then we have a disk. So this one 1 plus 1 minus 1 minus 1. Okay, and so this is the set B2. Okay, circle radius 1, yeah. And now what happened if I replace B2 by B infinity? So now my new set is B infinity, yeah. B infinity is x in, just a vector x, yes, and infinity less than or equal 1. So it just equal x1, x2, and now max of absolute of x1, x2 less than or equal 1. So what is this set? Again, I draw x1 and x2 here. So what is this set? How does it look like? Anyone? So max of the magnitude of x1 and x2 less than 1. So how does it look like? So it's not a diamond, it's not a circle. Well, I mean, we can do it again. The region between x is plus or minus 1. Yes, correct, yes. So you can see that if you have a square like this, yeah, then everything inside this square, when you take the absolute value, right, it will be less than or equal 1. Okay, so inside this, you take the maximal value just less than or equal 1. Okay, so x1 is between minus and plus 1, and y is between minus and plus 1. Okay, so you get the idea, right? Okay, so the next question is, show that, so 3, show that the 2 norm of a vector x is less than or equal the 1 norm of the vector x. All right, 1 norm, yeah. Less than or equal square root n times the 2 norm of the vector x. So essentially just say that, okay, somehow you can compare the 1 norm and the 2 norm by those two constants, 1 or square root n. Okay, so how do we do that? So for example, if I take, suppose I just take n equal 2, right? I just take a simple case. N equal 1 is obvious, right? N equal 1, you just have a single number. Yeah, but n equal 2, okay? Then the 2 norm of x will be x1 square plus x2 square, right? Well, squared, maybe squared. I want to square, yeah. And then what is the 1 norm of x? Well, the 1 norm is just x1 an absolute value plus x2 an absolute value. Okay. And now if I square this, then what do I have? Then I have x1 square plus x2 square plus 2 absolute value of x1, absolute value of x2. Right? So you see it obvious that the norm of the 2 norm, I mean the square of the 2 norms is less than the square of the 1 norm. Yeah, because you have this extra term here. Yeah. Right? So in this case, then the 1 norm is just greater or equal to the 2 norm. Okay? So just expand it. So you do the same in general for general n, yeah? So general n. So, you know, I mean, you start proving with a simple case first, and when you see the idea, then you can do the general case. So general n, then you have x, 1 norm is x1 up to xn in absolute value, right? And now when I square it, okay, then you can have x1 square plus x2 square xn square plus 2 now on the cross term, yeah, to x1, x3, and so on. You know, I mean, cross term, yeah. So we know that there's a lot of cross terms, yeah. but we don't worry because you just add on some positive numbers. So this one definitely greater or equal x1 square plus x2 square up to xn square. And this is your 2 norm square. And that's it. Okay. So at least we prove one inequality. Yeah. So we prove the 2 norm is, we prove at least one inequality. Yeah. So we prove this part. The 2 norm of a vector is always less than the 1 norm of a vector. Yeah. So now the other part. So this one is like inequality 1. Yeah. So inequality 1. So now how do I prove inequality 2? Okay. So how do I do inequality 2? Okay. So maybe let me introduce you an inequality. Okay. So maybe you've seen it before. Maybe you haven't seen it before. But now let me write down to you. So first, suppose I have 2 vectors, A and B, in Rn, right? Then what happens if I take a dot product of 2 vectors? Then, have you seen this formula before? So it will be the length of the vector A. So the length is the 2 norm, right? Times the length of the vector B, times cosine the angle between vector A and B. Have you seen this equation before, this relation? Somewhere. So the dot product of 2 vectors can be written as, we haven't seen this. In linear algebra? Yes, in linear algebra, yeah. So linear algebra, you see this formula, okay? So the dot product can be written as the length of the 2 vectors times the cosines between the 2 vectors, okay? So then you see that the cosine is always less than or equal 1, right? So now what I'm going to do is I'm going to make it less than or equal the length of the 2 vectors. Okay, so because the cosine is always less than or equal 1, right? So you just make the maximal, so then it's less than or equal. So the dot product of 2 vectors less than the product of the length of the 2 vectors. And I think there's a name for this inequality called Cauchy-Schwarz inequality. Okay. Or some Russian can say that Cauchy-Schwarz Bunyakovsky inequality. Okay. So now I'm going to use this inequality. Yeah. So let me show you how I'm going to use it. So now I'm going to use A to be the vector that has the entries to be absolute value of x1, absolute value of x2, up to absolute value of xn. Okay. You see it? So now if I plug into this inequality, then I will have the length of the vector x here, the 2 norm here. Yeah. So now what vector b should I choose? So that the length of the vector b is square root n. And on the left, you have just the 1 norm of the vector x. So what is the vector b look like? How do I choose vector b? So how do I choose vector b? Anyone? So remember a dot b, yeah? So A dot B is just equal A1, B1, A2, B2, AN, BN, right? And now, if I choose A1 to be absolute value of X1, then I have this one, X1, B1, X2, B2, XN, BN. Yeah, B equal NA. Well, if B equal NA, then this one gives me X1 square. No, I want the one norm. You see, on the right hand side, I have the two norm already. On the left hand side, I want the one norm. So if you put B equal NA, it doesn't give you the one norm. Something simple, something similar. One, yeah. Just choose B to be one. Okay. Yeah. Then this one just give you the one norm. You know, one, yeah. X2, Xn. So it gives you the one norm of the vector X. Okay. And then what is the length of the vector B? Well, the length of the vector B is just square root n. Right? So therefore, if you apply the Cauchy-Schwarz inequality, so then you have A dot B equal the length, I mean the one norm of X less than or equal the length of the vector X in the two norm, yeah? So the length is the two norm, but the one norm is not the length, yeah? Times square root n. So that is exactly the inequality. Okay. So that is the trick. So you choose A and B in a special way. So then you can apply Cauchy-Schwarz inequality. Yeah. So I'm going to leave the remaining two inequalities as an exercise. You can do it. Okay. Otherwise, you can ask me. But the other two inequalities are not tricky. So now we move to question 2. Question 2 is a bit tricky. Yeah. So question 2. What the question want you to prove is 1 over n kappa 2 of the matrix A less than or equal kappa 1 less than n kappa 2 matrix A. So remember kappa 2 is just a condition number in the two norm of the matrix A. Okay, so this one is just the norm of the matrix A times the norm of the matrix A inverse. Okay, in the two norm. Yeah, so this is a definition, yeah. And now what is the two norm of the matrix A in the definition? It's a max of V not equal 0, the AV, the two norm divided by the V, the two norm, right? Okay. But now, so if you remember, you know, we proved that the two norm is less than the one norm, right? So now I have the AV that is less than the, so this is a two norm, right? We're less than AV in the one norm. We just proved it in the previous question. Okay. And then I also have the V norm in the two norm, right? Is bigger or equal 1 over square root n V in the one norm. So remember we proved it in the previous question. So if you remember, so this is the previous question. We proved this inequality, yeah. So the 2 norm is less than the 1 norm. Okay. But you read this inequality backward. The 2 norm is bigger than 1 over square root n on the 1 norm. So that exactly here. Okay. So that is exactly. So now I take the ratio. So if I take the ratio, then I have AV over V less than or equal AV in the 1 norm over V in the 1 norm divided by square root n. So become multiplied by square root n. Right? And now remember, if we take maximal over V, yeah, if you take maximal over V, then this one becomes the 1 norm. So then if you take the maximal, then this one becomes the 1 norm of the matrix A. Okay. So you see, I mean, for a arbitrary vector V, yeah, then it's less than the maximal of this ratio over on V. And the maximal over on V is just a 1 norm. Okay. And now if you take the maximal on the left, so now if you take the maximal on the left, then so now you take the maximal, you take the max AV 2 norm over V on the left, then it's less than or equal square root n times the 1 norm here. Okay, and this one is actually just a 2 norm, the matrix. Okay, so what you have done is you prove that the 2 norm of a matrix is less than or equal square root n, the 1 norm of a matrix. Okay, so before we prove our vectors, but now we prove for a norm of a matrix. Yeah. So then what do I have? So if I write down what we have done, yeah. So we have the 2 norm of a matrix A less than or equal square root n of the 1 norm of matrix A. And you can do the same for A inverse. Okay, so if you replace A by A inverse, then exactly the same arguments can be applied, and you make A inverse, the 2 norm less than or equal square root n A inverse in the 1 norm. And now you multiply them together. If you multiply 2 things together, become condition number in the 2 norm of the matrix A. Okay, less than or equal square root n times square root n become n. Condition number in the 1 norm of the matrix A. Okay, so we prove one inequality. So remember, we proved one inequality in the question. Yeah, so the question actually say that 1 over n kappa 2a less than or equal kappa 1a, but essentially it's just the same, yeah? Just multiply or divided by 1 over n. Okay? And now we need to prove another inequality. So I'm going to do the same trick. Okay, so before, so while the difference is now I will have AV 2 norm, right? So remember before I make it less or equal, the 1 norm, yeah? But I don't want that. Now I want to use another way. So I say that, okay, the 2 norm is greater or equal 1 over square root n, the 1 norm of AV, okay? And then V, the 2 norm less than or equal the one norm of V. Okay, so I just use the other way of the inequality. And now I take the ratio. So I got AV divided by V greater or equal 1 over root n AV in the one norm over V, the one norm, right? Okay, so now it's a bit tricky. So now if you take the maximal, right, maximal of this one, then it will be less than or equal the two norm, right? So this one will be less than or equal the two norm. Yeah, remember this one is just a maximal, right? Take the maximal. So then this one has the less than or equal the two norm, yeah? And now, because it is correct for every vector v, so now you can say that now the two norm is greater or equal 1 over root n max of AV1 over V1. Yeah, because it's true for every vector v. Okay, and so this one will be your one norm of the matrix A. So now you prove that A, when you take the two norm, is greater or equal 1 over root n times the one norm of the matrix A. Okay, and now you do the same for the inverse. Okay, so you have A inverse, two norm greater than or equal 1 over root n A inverse, the one norm. Right, so you multiply, now after that you multiply, you got the condition number in the two norm is greater or equal 1 over n, right? Because now you multiply square root, 1 over square root, and with 1 over square root n, so you got 1 over n. The condition number and the one norm of the matrix A. Okay, so that is another inequality. Okay. So is it understandable? So this one is just linear algebra, but you know, another twist with the definition of the norm of the matrix. Yeah. So any question? So far, so good? No question? Everything is crystal clear, yeah? Okay. It'll be clear after watching it 6 times. Okay. Well, remember, you see, I've been teaching like 7 years or 9 years already, you know, so I'm talking about this more than 6 times, you know. So, okay. So now what is the next question? So the next question is, the next question essentially what we have done in the lectures already. So I will skip the next question, yeah? So now we go to question number 4. So number 3 has been done in the lectures, yeah? So now I'm going to do question 4. So question 4 say that we have a symmetric matrix, and then you have the eigenvalues are given like this. So the eigenvalue of A, okay, is 1004.2, 999.8, and so on. So we just worry about the largest and the smallest. So it's order like this, yeah? And now why A is non-singular? So remember A is non-singular. when determinant is not 0, okay? It's not 0, so this is a definition of the non-singular matrix. And in our case, what is a determinant? So determinant is a product of all eigenvalues. So this one is a result in linear algebra, okay? So I assume that, we can use the results in linear algebra. So I don't remember how to prove it, but I remember the results, okay? But I can look it up. But then now what we need to use is, okay, so lambda 1 is just 1004.2 something, yeah? And it's a positive number. And the last one is still a positive number, okay? So remember, this is the smallest eigenvalues. So the product is still positive. Okay, so therefore the determinant is non-zero. It's positive, it's non-zero. So therefore A is non-singular. Okay, so this is explain why A is non-singular. And now back to our material. So what is the condition number of A? So here we have to understand this is a condition number in the two norm, right? So here we can use the theorem in the lectures. It's just the maximal eigenvalue in absolute value divided by the smallest eigenvalue in absolute value. Okay, so this is the theorem in the lectures. And then the maximal eigenvalue just 1004.2, and the smallest eigenvalue is 0.0005. And you plug in MATLAB or your computer, and then you got 2,008,400. Okay, so that is can be done. And now the next question is, what is the relative errors in the inputs A and B? So what is the relative errors in the matrix A? Well, if you read the question, you will see that A is known exactly. Okay. So if A is known exactly and A is a real matrix, then the relative errors in A is just epsilon. So epsilon is a machine by epsilon, remember? So 2.2 10 to the minus 16, yeah? And if A is an integers matrix and it's known exactly, then relative errors will equal 0. But we don't have this assumption. So we are just assume that relative errors is just the machine by epsilon, yeah? And now if you read the question again, there is a phrase called B is measure to 6 digits. Okay. So this just means that the relative errors in B is less than 0.5, 10 to the minus 6. Okay, so 6 digits, 10 to the minus 6. You have 7 digits, then you have 10 to the minus 7. Okay. And now what is the relative errors in the linear system AX equal B? So relative errors in X will be less than or equal. So this is the theorem in the lectures. So condition number of A, okay, multiplied by the relative errors in B, or maybe in the matrix A first, yeah, plus the relative errors in B. And now we have all those information, so you just put it in. So the condition number is about 2 million, yeah, so about 2 million here. And the relative errors in A is 2.2, 10 to the minus 16. And relative errors in B is 0.5, 10 to the minus 6. So you see that this quantity is very smaller than this one. Okay, so the errors will come from the second terms. So this one about 2 million, this one is about half of 1 over a million. Yeah, so you can see that it will cancel out and it give you 1.0042. Okay. So what is the relative error? So remember the relative errors in X, it's just X minus the approximation of X in the two norm divided by the two norm of the vector X. So even the matrix not exactly, there's still errors of epsilon. Well, that's what I say. It's a good question. You see, if a matrix is not exactly, but it's a floating point number matrix, it's a real matrix, then when you store into a double precision system, then it still have the errors of epsilon, right? Because suppose, I mean, the matrix, the value is 1/3, but you cannot store 1/3 exactly inside any floating point system, okay? Or say 0.1, you have infinitely many digits and you have to cut off at 52 digits. Then you have some errors, yeah? So that's why I say only if the matrix is integers values, then you can store exactly and the errors will be equal 0. But here they don't say that the matrix is integers. Okay, but so we just assume that it's a real matrix. It's a good question, yeah? Okay, so now go back to this calculation. So now if the errors is, the relative errors is 1.0042, then is it a big or small errors? Because, I mean, it's related to the next question. So what confidence do you have in the, yes, it's very big. Remember, it's the relative errors. Just like the errors is the size of the vector X, right? When you cross multiply, you got 1 multiplied by the length of the vector X. So like if I try to measure the length of the pen, of my pen, then the errors is the same size of the pen, right? Very big. I mean, nobody will use the results. Okay, so the condition number of the matrix plays a very important role here. So if you have an ill conditioned matrix, then the solution doesn't make any, doesn't have any accurate results. Yeah. So any question? Any further question? Okay, so number 5 is about LU factorization. So suppose we have a matrix. Suppose we have a matrix A is LU factorization. So you have A is 2 minus 2, 3, and minus 10, 3, minus 11, 4, 3, 3. Yeah. So you just apply, so find the LU factorization without pivoting, yeah? You just apply row operation. So now if you apply row operation, row 2 minus 5, so become plus 5, yeah? Row 1. Then you have, so this one becomes 0, minus 7, and 4. Okay, so this is row 2. And row 3 minus 2 row 1. Then this one becomes 0, 7 minus 3. Okay. And now you do another operation. So row 3 Well, just plus row 2, right? Then you got 2 minus 2, 3, 0, minus 7, 4, 0, 0, 1. Okay, then you stop. So this is your upper triangular matrix. Yeah. So without pivoting, you see, without swapping any rows. So in this case, then you have a matrix U is like this. And what is a matrix L? So remember L, you just collect the coefficient from the operation, so from the row operation. So in this case, I collect L from here, so minus 5 and plus 2. Yeah, so minus 5 and plus 2. Right, so I just collect from here. So remember, so you collect from this operation. Okay, and then this one is just minus 1. Yeah, so you can check. So check that A equal LU. So in this case, A equal LU because there's no permutation, no swapping. So use the results to find A inverse. So how do we find A inverse? So remember A inverse is just a solution of AX equal identity. Right, but in our case, you know, you can have LU equal A, right? So LUX is identity. Okay. And so now we can solve, you know, UX equal Y first. So you have LY is identity, then UX equal Y. Okay. So now, how do I solve LY is identity? Well, so we can do step by step, yeah. So solving, so I say step 1, yeah. Step 1 is LY equal identity. So now let me do step 1 first, yeah. So LY identity is the same as, so remember you have the matrix 1, 0, 0, so the matrix L minus 5, 1, 0, 2 minus 1, 1, yeah. And then you got Y11, Y12, Y13, Y21, Y22, Y23, Y31, Y32, Y33. Equal identity, 1, 1, 1. Okay. Then, so how do I solve it? Well, I just, you know, I mean, take the first column here. Yeah. And I write down system. I can write down system. So my system will be Y11 equal 1, right? And then minus, so this one is, I multiply this, yeah? And then minus 5. So the second one is minus 511 plus 1, Y12 is 0. And then the last one is 2Y11 minus Y, sorry, the last one is, yeah, 2Y11 minus Y21 and plus Y31 equals 0. Okay, so now I just use forward substitution. So Y11 equal 1, so it's okay. So then Y21 is 5, Y11 is 5. And here, Y31 will be minus 2 plus 5, so equals 3. Okay, so now I have the matrix Y is the very first column is just 1, 5, and 3. Okay. And I can use the same techniques, yeah. So suppose I use the same technique and I got the full matrix Y like this. So I assume that I have done this calculation, yeah. And I got the matrix Y, yeah. And then after that, you solve Ux. So step 2, you solve Ux equal Y. Okay, so Ux equal Y. So Ux, remember Ux is the upper triangular matrix. Okay. And then you put in the matrix X, it's just X11, X12, X13, X21, X22, X23, X31, 32, X33, yeah? And equal the matrix Y. So the matrix Y is 1, 5, 3, 0, 0 here, 1, 0, 1, 1. Okay, so we use the same techniques, yeah? Now you just solve for the first column first, yeah? Okay, and now I have 2x11 minus 2x21 plus 3x31 equal 1. And I have 7 or minus 7, x21 plus 4, x31 equal 5. And the last one is just x31 equal 3. Okay, so now I can use back substitution. Yeah, so if I use back substitution, so back substitution, then this one gives me x21 will equal 5 minus 12 divided by minus 7. Yeah, so what is just 1. Okay, so you can check that. Yeah, and then this one gives me x11, yeah, will equal 1, then plus 2, yeah, because minus 2, so become plus 2, minus 3 times 3, so minus 9 divided by 2. Yeah, so it becomes 3, so minus 6, so divided by 2 by minus 3. Okay. So what do I have? So what do I have for the first column of the vector x? Sorry, of the matrix X. So the first column of the matrix X will be minus 3, 1, and 3. Okay, and if you use the same techniques, then you can get the other entries of the matrix X as well. And this one will be your inverse of the matrix A. Okay, so this is A inverse. So you can ask, what's the point to do this? Well, because suppose you see, you are asked to write a C program to compute the inverse of a matrix using the LU factorization. And at least you know how to do it, I mean, at least by hand first, and you can program it. But now, because now MATLAB, Python, everything is available, but at least, this one show you how the algorithm works, so you can implement it from scratch. Okay, because finding the inverse by LU factorization can be programmed easily. Yeah. So, any question? I think we don't have time to the next question.